the Leibnitz test statement and its proof, and it is for the alternative series. Now before that, let me define what is an alternative series is. An alternative series, a series is said to be an alternative series. A series is said to be an alternative series. A series is said to be an alternative series if it is a series with alternatively positive and negative terms, alternatively containing positive and negative terms. For example, the series of the form -1 to the power of n minus 1 an, where n running from 1 to infinity, will be equal to a1 minus a2 plus a3 minus a4 plus and so on, plus minus and so on. Here this is a series of the positive negative terms containing in it, and these types of series are called alternative series. Now to test the alternative series whether it is a convergent or not, we are going to use the Leibniz test. And what is the statement of the Leibniz test is, Leibniz test for alternative series. Alternative series. This series is going to use to check the convergence, and the statement of this series says that if the alternative series say summation n from 1 to infinity minus 1 power n plus 1 or minus 1 to the power of n minus 1 of an is equal to a1 minus a2 plus a3 minus a4 and so on, satisfies the following two conditions. Then this alternative series is convergent. Then what are those two conditions are? Those two conditions are, firstly, this is a decreasing sequence, monotonically decreasing sequence. The first condition is 0 less than an plus 1 less than equal to an should be true for all n equal to 1, 2 and so on. And the second condition is the limit of an as n tends to infinity is equal to 0. Then this alternative series is convergent. Now what is the proof of this? Now let us see the proof for this. The Leibniz test says that if the alternative series satisfies the following two conditions, say an plus 1 less than equal to an for all n is equal to so on 1 2 3 4 so on, and the second condition is the limit of an is equal to 0. Here the next term is less than the previous term. The next term is less than or equal to the previous term, means when the next term is going to less than, the series is a decreasing sequence. When your alternative series is a decreasing sequence and the limit of nth term is equal to 0, then according to this Leibnitz test, it says the series is a convergent. Now let us have a look at the proof of this proof, and to prove this, we'll consider the alternative series which satisfies these two conditions. Now let the summation minus 1 to the power of n minus 1 of an, where n running from 1 to infinity, this is n minus 1, let this also be the n minus 1, is equal to a1 minus a2 plus a3 minus a4 plus minus and so on b given alternative series, be the alternative series with the condition that an plus 1 less than an for all n equal to 1 2 3 4 and the limit of an as n tends to infinity is equal to 0. Now I have considered the alternative sequence. Now alternative series. Now I need to, with this two condition, now I need to show that this alternative series is a convergent. Now to show that the series is convergent, it is enough to show that the nth partial sum of the series is convergent. The sequence of nth partial sum of this series is convergent. And again, to show that the sequence of nth partial sum of this series, I am going to use the fact that every monotonically increasing and bounded above sequence, monotonically increasing and bounded above sequence is convergent. Now let s of 2n be the partial sum of 2n terms of the series. That is, my s of 2n have the element of a1 minus a2 plus a3 minus a4 plus so on up to plus minus plus a2n minus 1 minus of a2n. S of 2n denote the partial sum of 2n terms, and again it is nothing but a1 minus a2 plus a3 minus a4 plus a5 minus a6 and so on plus a2n minus 1 minus of a2n. And if I combine the terms like this, combine these two n terms like this, the quantity in each bracket is greater than 0, is greater than 0, because the condition 1 says that the next term is less than the previous terms, means this is less than this one, this is less than this one, so that each terms are positive. Each terms are positive implies s of 2n is positive. S of 2n is a positive terms. And now consider, if I consider s of 2n plus 2 minus of s of 2n, what I will get is a of 2n plus 1, a of 2n plus 1 minus of a 2n plus 2. And again, by this condition, again the above condition, each terms, this is greater than this one, therefore this is positive, implies s of 2n plus 2 minus of s of 2n is greater than 0, implies the sequence of partial sum of s of 2n is monotonically increasing. Now if we show that this sequence is bounded also, then it is a monotonically increasing and bounded, so that it will be convergent. And again, if I consider again s of 2n in the pattern of a1 minus a2 minus a3 minus a4 minus a5 minus so on minus of a2n. And here if I take the negative here like this, now if my s of 2n is this term, now what is the value of s of 2n is? This s of 2n value will definitely be less than this a1, because this is positive and this is also positive. Each terms in between the brackets are positive, and as this is the positive with the negative, positive with the negative, so this entire terms will be x, say negative, means a1 minus x, s of 2n is equal to a1 minus of x, means this s of 2n is less than a1, this implies s of 2n less than a1. This is 2. Now from equation 1 and equation 2 we have proved that the sequence s of 2n is convergent as it is monotonically increasing and bounded. See this from equation 1 and 2, and from this what we can write, this is greater than 0. When it is greater than 0 and less than a1 means s of 2n is bounded. S of 2n is bounded, therefore the sequence of s of 2n is convergent. Similarly it holds for s of 2n plus 1, therefore will be same as the limit of s of 2n and s of 2n plus 1 will be same. Now to show that limit of s of 2n is equal to limit 1 will be same. Consider let limit n tends to infinity, s of 2n is equal to L, and equal to L, if I consider S of 2n plus 1, which will be equal to S of 2n plus A of 2n plus 1, A of 2n plus 1, then if I take the limit to this one, limit n tends to infinity of S of 2n plus 1 will be equal to limit n tends to infinity of S of 2n plus A of 2n plus 1, and this will be equal to limit n tends to infinity S of 2n plus 1 will be equal to limit n tends to infinity of S of 2n plus the limit n tends to infinity A 2n plus 1. Now from the consideration, this will be L and this will be 0 by hypothesis or by the consideration, by the given condition. This implies the limit of S of 2n plus 1 as n tends to infinity will be equal to L. Therefore, with this it shows that the sequence Sn is converges to L. Hence the summation n from 1 to infinity minus 1 to n minus 1 of An is convergent. Now with this we can conclude the